What we need to talk about is a new rule, well, a more complicated derivative and a new rule. You got the handout there on this. Yeah, it just turns out there's some derivatives that are more complicated than others, and you'll see why that is so in just a second. I'll put it up here, but let's first of all, let's just start with kind of a reference point, what the derivative of y equals the square root of x is again. So y equals the square root of x, the derivative is then, well, again, turn that into 1/2 power, right? X to the 1/2. So the derivative is 1/2 times x to the minus 1/2 is one form of it. And we could change it into other forms, but let's just go with that, leave that. We'll refer back to that in just a second, okay? Now, the more complicated derivative, it's related to the square root of x, the one I'm going to start with here, but it's y equals the square root of x squared plus 3x. Yeah, so it's a square root. However, this one's much more complicated because it's the square root of x squared plus 3x. And I guess the first thing to note, I may have noted it before, but I can't split that up. The square root of a plus b, unfortunately, does not equal the square root of a plus square root of b. If that's what you're thinking, I can just split that up. You can't split that up. So it has to be, it's going to have to be that form right there. But I want to know what the derivative of it is. And so on the handout, what I've got is, let's just go through it with the limit definition. There's, on the test coming up, you will have to do a couple of them with the limit definition. So for one thing, it doesn't hurt to practice a little bit, go through those time to time. But the other thing is it'll pay off in the end. We can see maybe what kind of rule we can build out of this, okay? All right, so let's go with the limit definition. It's the limit as h approaches 0, f of x plus h. This is all on the handout there, so to write all this, but you got that. All right, so that's our limit definition. What does it mean? Well, it means I'm going to plug in, first of all, I'm going to plug in the x plus h. So that's going to give me y prime equals the limit as h approaches 0. So that'll be the square root of x plus h squared plus 3 times x plus h. Both of those x's are replaced by x plus h. Then I subtract f of x. Well, that is f of x. Y is the f of x. So subtract the square root of x squared plus 3x, and then divide that all by h. And so on line 3, I'm going to go ahead and combine it with my line 2 here, but on line 3, what do we do to figure that derivative out? Well, that's one where we do the conjugate, isn't it? So on line 3, fill in the blanks there, we're going to multiply top and bottom here by the conjugate. So it's the square root of x plus h squared plus 3 times x plus h plus, so we just change the minus to a plus there, the square root of x squared plus 3x, top and bottom. Right? Does that make sense? Okay. Well, of course, what that does, so for line 4 then, when I multiply, right, the conjugates on the top together, what happens? Well, this times this, those square roots cancel, so I have the limit as h approaches 0 of this times this without the square root, right? So it'd be, or the square roots would make it just be x plus h squared plus 3 times x plus h. That's the first part of that. And then the middle terms drop out. And then this times this, the square roots cancel out, so I have minus the x squared plus 3x. That's what I've got on top there. And then on the bottom, I've got h times, well, I got that conjugate on the other side of it. All right, so what's next? Well, there's a little canceling that we're simplifying first of all. So what I did on line 5 there is I went ahead and multiplied this out. x plus h squared out, so it'd be x squared plus 2xh plus h squared. Distribute the 3, so it'd be 3x plus 3h. And distribute the minus, so it'd be minus x squared minus 3x all over this h times square roots here. All right, nice things happen. I didn't mark them out, but the x squareds, got an x squared minus an x squared, we got a 3x and a minus 3x, and so that leaves us these three things, and so that's why on line 6 I have that h, they all have an h in them, so I'm going to factor off that h, and then it cancels nicely with the h on the bottom there. So we have h times, 2x plus h plus 3. All over the h times that square root stuff. But yeah, the h's cancel. And, I guess I should write it. Because I went ahead and then, on line 7, is it on line 7 now? That's why I let y'all have this handout so you wouldn't have to write. You'd follow me, but you didn't have to write on this. All right. So on line, where are we? Line 7 now. So I've got rid of the h's. What can I do? Now I can plug in h to be 0 because the denominator does not go to 0 now. Plug in the h to be 0, so 2x plus 0 plus 3, so it'd be 2x plus 3. H is 0, so that'd be x squared plus 3x, square root. That one doesn't have an h in it, so it's x square root of x squared plus 3x, but this, on the denominator there, those are like radicals, so I can add them. I got one of those plus another one of those, so there's 2 of those. So I got 2x plus 3 for line 8 over 2 times the square root of x squared plus 3x. So far, so good. Make sense so far? All right. Well, on line 9, what I did is I separated this out a little bit. Basically, on line 9, all I did was I pulled that over to the side there and put a 1 over 2 times the square root of x squared plus 3x. But I pulled that 2x plus 3 over. And then for line 10, here's what I get. Y prime equals 1/2 times x squared plus 3x to the minus 1/2 times 2x plus 3. Here's why I write. I mean, this was a perfectly fine end. I mean, if we were working that, that's where we would stop. However, because of what the rule that we're going to talk about, let's rewrite it this form. So it's just 1/2. You can see where that came from, and then yeah, that square root's in the denominator, so it'd be a minus 1/2 instead of a positive 1/2. It'd be minus 1/2. Does that make all sense? Make sense? Okay. All right, so we started with y equals the square root. Let me write it close by here. And that's where comparison comes in. Let me write that over here so you can really see it. All right, so for comparison's sake there, don't you see a lot of comparison between these two derivatives? This one's 1/2 x to the minus 1/2. Well, I've got a 1/2, and then I've got a minus 1/2 power, don't I? Now the inside here, obviously, is different, but that's because we started with something different. So hopefully you see here, that's that derivative of that 1/2 power, isn't it? Just like this is x to the 1/2, and so this came from that being a 1/2 power. Well, that's what I've got here, don't I? It's x squared plus 3x to the 1/2 power. So that makes sense, doesn't it? I've got a 1/2 power, I've got to do the derivative of it, which gives me, bring down the half, make the new power minus 1. Okay, so that makes sense. Now, the only question is, you know the answer already, You've seen this before. Don't let on. Let them think about it a little bit. Where does that come from? You see where that might come from? 2x plus 3. Well, think about right in here. X squared plus 3x. What would be the derivative of x squared plus 3x? It's 2x plus 3, isn't it? Yeah, this is the derivative of what's inside the square root here. The derivative of the inside. Here's the way I like to break this down. What I've got then is I've got an inside and outside scenario. I've got stuff on the inside and I've got a power on the outside. So I've got an inside operation and an outside operation. The x squared plus 3x is, like I said, the inside. And the 1/2 power is the outside. So what this breaks down to be, this derivative I've got, is this right here. What I did is I did the derivative of the outside. That's the derivative of the outside. The outside is 1/2 power, so I brought down that power. The new power is negative 1/2. Then I multiply that by the derivative of the inside. Now, one other extremely important note is when I did this derivative of the outside, what happened to the inside? When I was doing the derivative of the outside here, what happened to the inside? Nothing happened to it, right? It stayed the same, okay? So the derivative of the outside, inside stays the same. When I'm doing that derivative of the outside, I keep the inside part the same. I do separately then a derivative of the inside. Okay? This is more or less what we call the chain rule. This is an example of the chain rule. Chain rule, new rule, to add to our list of rules for derivatives. It's called the chain rule. In the chain rule, what I do is I use that. When do I use it? When I have a similar situation. When I have a function that has an inside and an outside part. Meaning an inside part that's not just plain x. I mean, this, I guess technically you'd say there's an inside and outside here, but the inside is just the x. But we're saying something's more significant, more complicated on the inside, and then you also have an outside. That's when you use the chain rule, when you have an inside, outside. And what is the chain rule? It's basically what I've got stated there. We'll write it in a little different format here, but basically that is what the chain rule is. All right? So let's write it out in sort of a more technical way, I guess. Yeah, so we've got an inside and outside part. How do we write that in kind of some notation? Well, here's for y equals f parentheses g of x. So you kind of see, hopefully there, what I'm doing there. What I'm saying is I've got an inside and an outside. I've got an inside function and an outside function, okay? The inside is the g, the outside is the f. So it's very similar to that. The chain rule says the y prime, the derivative is then, but what was it? It's the derivative of the outside, inside stays the same. So the derivative of the outside would be f prime. The inside stays the same. So we just do the f prime, g of x. And then we multiply it by the derivative of the inside. Well, the inside is g of x, so I do it times the derivative of g of x. That's how we can write it, which may help you, may not. But here's what to remember. This right here, that's the derivative of the outside with the inside staying the same. Times, this is the derivative of the inside. That's the chain rule, okay? It's the derivative of the outside times the derivative of the inside. That's a very simple way to put it, but more or less that's what it is. You're just doing the derivative of the inside, derivative of the outside, and then multiplying it separately by the derivative of the inside. Okay? Another way to look at it, this will be helpful for some examples later that I will do, but basically what this is saying is I've got a 1/2 power, so I've got to do the derivative of it. I've got stuff on the inside. Basically, I've got to take the derivative of everything, in the proper order, but I've got to do the derivative of this, I've got to do the derivative of everything I've got there, okay? That's more or less what it is. Every operation I've got there, I've got to at some point do the derivative of it. I've got a 1/2 power, so I've got to do the derivative of that. On the inside, I've got x squared plus 3x, so I've got to do the derivative of that somehow or some way, okay? And this is how you do it. All right? Shall we try another? Let's try another. All right? It is helpful. All right, let's do this one. All right, so let's say we've got f of x equals 5th root of x squared minus 2x minus 9. One thing that's helpful in this chain rule is if you can write it with parentheses. And of course, that's what we're going to do here, is write this with parentheses. It would be x squared minus 2x minus 9 in parentheses to what power? Well, it's 5th root, and so let's write it. 1/5 power. Right? 5th root is 1/5 power. Yeah, so what I'm saying is, with the parentheses, it maybe is pretty obvious anyway, but with parentheses, it's very obvious. The inside and the outside part, you got x squared minus 2x on the inside, the 1/5 power on the outside, no doubt about it. So when I go to do this derivative, how does it work? Well, I've got an inside and outside part, so I've got to do those derivatives separately. Start with the derivative of the outside. First of all, I'll do the derivative of the outside. The outside power is 1/5. Power rule, so I bring down the power, make it 1/5 times. Now what happens when I'm doing the derivative of the outside, what happens to the inside? Leave it alone. Don't change it. So derivative of the outside, the inside stays the same, x squared minus 2x minus 9. Then the new power, well, it's 1/5, so I subtract 1, 1/5 minus 1, negative 4/5. That's 5/5, so minus 1/5 is the new power. Okay, that's my derivative of the outside. Times it by the derivative of the inside. Well, that's a whole lot easier. The derivative of the inside is just 2x minus 2. No. You can clean it up a little bit. I mean, you can make the negative exponent positive with 2x minus 2 on top, but I'm okay with that. All right? All right, now, when we get to the trig functions, let's talk about this chain rule with some trig functions, because that's another place you'll see these a lot. Yeah, say I've got y equals tangent of 2x. You might be saying, well, is that a chain rule? Yeah. Usually this is the form we see it written, tangent of 2x. However, There is some parentheses there, understood to be some parentheses, and I think it's helpful, especially starting this out, if we put those parentheses back in there, use those parentheses. Parentheses would be around the 2x. So if you see there, I've got an inside and outside. The inside is something more than just x. It's not just tangent of x, it's tangent of 2x. And so that 2x, that's a more complicated matter than just x. And so this is another chain rule. Because what have I got? I've got tangents on the outside, 2x is on the inside. Yeah, this is chain rule. It's a pretty simple one, but it is what it is, okay? So let's get the derivative. How does the derivative work? Well, derivative of the outside times the derivative of the inside. So the derivative of the outside, the tangent's on the outside. Got to do the derivative of the tangent first. Derivative of tangent, secant squared. Now this is important too. When you do the derivative of the outside, inside stays the same. So this is secant squared, inside stays the same. So the inside is still 2x. Now I do the derivative of the inside. Well, that's a simple derivative of 2x. Derivative of 2x is just 2. So you have secant squared 2x times 2. All right, what can I do with that 2? Not a whole lot, because I can't put it's secant squared 2x, so that 2 I can't pull in there, multiply that in there. Usually what you'll just see is you'll see the 2 in front here. So that's my derivative. 2 times secant squared 2x. All right? Now this one, well, let's do another one very similar, and then we'll compare it to another one. All right, so let's say we got sine of x squared. I want to do the derivative of sine of x squared. Well, hopefully, obviously there, we got an inside and outside. What's inside, what's outside now? Well, again, the parentheses help us out. The x squared, the parentheses is usually inside. And the sine's on the outside. So, similar to the one we just had, but so I do the derivative of the outside, derivative of sine is cosine, inside stays the same, so it's still cosine of x squared. Then I multiply it by the derivative of the inside. The derivative of the inside is x squared, so the derivative is 2x. Cosine x squared times 2x. And again, we can't multiply the x squared and the 2x because the x squared is in the cosine. Usually they'll write the trig function last, so that's probably how you would see it. You don't have to, but just FYI. Okay? Pretty simple. We'll get to some more complicated here in a second. But let's compare that one to this. Y equals cosine to the 5th t. Cosine to the 5th t. Well, for one thing, this one is probably not in the most advantageous, let's call it, form, because it doesn't have the parentheses. This is a nice way to write this function, cosine of 5th t, but it's more helpful to write it out descriptively here with parentheses. Cosine of 5th t, what does that mean? That means I want the 5th power of cosine of t. That's what that means. So in other words, I want cosine of t to the 5th power. That's what that means. This is just a nice way of writing it. But that's what it means. Now do you see why this is more advantageous to write it? More to our advantage? Because that shows us our inside and outside, doesn't it? Obviously. This one's just kind of the opposite of what this one was. Because what's on the inside here? And what's on the outside? Over here, the trig function was the outside. Over here, it's on the inside. So you see the difference? The inside is cosine t. The outside is 5 power 5. So what's my derivative? Derivative. So I do the derivative of the outside, which is the 5 power. So it's just power rule. Bring down the power of 5. Inside stays the same, so the inside is still cosine t. But the new power, 1 less, so it's cosine t to the 4th. That's the derivative of the outside. Don't forget though, you have to do the derivative of the inside. Derivative of the inside is derivative of cosine t. Derivative of cosine t is negative sine t. Yes? With me there? So that's a pretty good answer. Clean it up. I would probably say, if we've got two numbers here and here, they usually multiply those. This is a negative 1, is what I'm saying, times 5. If it's a 2 or 3, they usually multiply those numbers together. So let's make it negative 5. We can make that, write that the pretty way there. Cosine t to the 4th is cosine 4th t times sine t. That's how they probably clean that one up. All right, let's do one more of these similar. All right, let's say we got y equals cotangent 5 theta plus secant 4 theta plus 3a. Cotangent 5 theta plus secant 4 theta plus 3a. I don't know if it's necessary here, but let's go ahead and write those with parentheses. Parentheses, if I put parentheses on these, it would be around the 5 theta and the 4 theta. So it would be cotangent, parentheses 5 theta plus secant, parentheses 4 theta plus 3a. Now, this is going to be multiple, right? So I've got multiple chain rules. So I've got an inside and outside here, and I've got an inside and outside here. The good news is, though, these are separated by pluses, and so there's not a rule there. You just do the derivative of this, plus the derivative of this, plus the derivative of this, right? Because it's pluses. Pluses and minus, you just do those straight up, okay? All right, so let's do these individually. All right, so here I've got cotangent. That would be considered the outside because the 5 theta is on the inside. So the derivative of it. So we have to remember derivatives of our trig functions. Cotangent, anybody remember? Tangent is secant squared. Cotangent is negative cosecant squared. So the derivative of cotangent is negative cosecant squared. And then the inside stays the same, so it'll be negative cosecant squared 5 theta. Yes? But what do I have to multiply that by? Well, I have to do the derivative of the 5 theta, don't I? And theta is like x, so it's 5x. Derivative of 5 theta would just be 5, wouldn't it? Because the power, that's theta to the first, so the new power would be theta to the 0, so it's just 5. With me? Good? All right, now we do our secant. All right, so this is important too, because of what happens. So this one's the same deal here. I've got the outside is the secant, the inside is the 4 theta. So I need to do the derivative of the outside and the derivative of the inside. The derivative of the outside. Well, the derivative of secant x is secant x tangent of x. But, all right, so ddx of secant x is secant x tangent x. Well, I do have a little complication here in that I've got secant, not x, I've got secant 4 theta. But, again, noting that when I do the derivative of the outside, the inside doesn't change. Inside stays the same. So if I have this as 4 theta, guess what these are? These are 4 thetas. With me? So the derivative of the outside, secant 4 theta, is secant 4 theta times tangent 4 theta. That's the derivative of the secant. Okay? See where I got that? But there's more to it. What else is it multiplied by? Well, it's multiplied by the derivative of the inside, which the inside here is 4 theta again, so the derivative would be just 4. Is everybody okay? Yes? Make sense? Now what about this? Bring back, this goes back to something we talked about earlier on derivatives. 3a, what's the a? If theta is our variable, a, b, c, those are considered constants. So this is 3 times a, but a is a constant. This is just a constant. So what's the derivative of the 3a? It's just the derivative of constant, which is 0. Oh, I guess I can leave that there because I'm going to clean this up. Is that right? So the derivative of that is 0 because it's a constant. A is considered to be a constant. So clean it up. Can't multiply the 5 because it's 5 thetas and the cosecant squared there. So let's just make it minus 5 cosecant squared 5 theta plus, usually I write the number first, so it'll be 4 secant 4 theta tangent 4 theta. I guess I don't have to write the parentheses either. I don't want to. I'll leave them in there. And then plus 0. That's it. That's my derivative.